Okay, so in order to understand this section, we need to recall the formula for variance of the sum of correlated variables. That should be familiar to you from basic probability, I think. So it looks like this. So variance of the sum of two random variables, say x1 and x2, is variance of x1 plus variance of x2 plus there is the third term. So if these two variables are uncorrelated, then that's it. Stop here. But if x1 and x2 are correlated, then there is the third term, 2 times covariance of x1 and x2. So what it tells us is that the variance of the sum of correlated variables, it has high variance if there is a high correlation between two variables. So I tried to experiment with it a little bit. So what are the correlations between different models? So let me explain what I did here. So I did, so first I did leave one out cross-validation, right? So what I did, I chose my training set to be 50 samples, well, 50, not 50 samples, sorry, 50 observations. 50 observations, of course. 50 observations in auto data set. And then I applied, so so which means that, so that there were 5 models, so like F hat. To train the first model, I removed the first observation and trained it on the remaining 49 observations, right? So 49 observations. So then to train the second model, I removed the second observation and trained it on the remaining 49 observations from these 50 observations, and so on, right? So F hat minus 3, F hat minus 4, F hat minus 5. So each of these models were trained on 49 observations from these 50. And then I applied it to each of these models. I applied it to construct predictions for 342 remaining, again, observations, not samples. So my whole sample is 392 observations. So I applied each of these 5 models to the 342 observations that it hasn't seen in training, right? So, and then I took correlations of predictions of these 5 models, so pairwise correlations. Like this is the correlation between predictions of model 1 and model 4. Now, to be honest, they are not precisely 1, so I just reported these correlations. So they're not exactly 1, so I rounded them to 3 decimal places. So the true numbers here are something like 0.00005 or something like this. But when rounded to 3 decimal places, they all become precisely 1. Okay, so then I did the same thing for 5-fold cross-validation. So in 5-fold cross-validation, so again, I have 5 models, F minus 1, F minus 2. But every time I trained these models, so I trained them on just 40 observations, 40 observations, not samples, yes, sorry about this. So which means that when you compare these 2 models, so each one is trained on 40 observations. So, and if you compare the training set used to train 2 different models, their overlap is 30 observations. So they always overlap, but the overlap size is not so large. And then again, I applied them to 342 remaining observations and compared and looked at the correlations. So as you see, the correlations became somewhat smaller. They're still almost perfect, to be honest. So maybe it's the property of this particular data set, I don't know, but it didn't change much. So correlations became a bit smaller. But the main idea here is that if we estimate a test error by just doing a single validation set, right? So which is 50% of all the available data. Then we tend to overestimate the error, right? So because our models are just not very accurate, since we only used half of the available data to train them. Leave one out cross-validation errors, so estimates, are almost unbiased because we used almost all data to train, almost all available data to derive this estimate. So k-fold cross-validation estimates are somewhere in between, right? Well, however, and this is probably kind of counterintuitive, and this needs explaining. So there is a high variance in estimating the test error using this leave one out cross-validation method. So what does it mean? Because on the first glance, it seems nonsense, because leave one out cross-validations are not random. So how can there be a variance if our method is not random? So this is how it goes. So imagine that we could generate, it is not random only because we always work with a single sample. So we just have some data set, and that's all that is available to us, right? But we assume that somewhere there exists like a true population that is much bigger. So huge true population from which we took our sample. Or maybe you can imagine that there exists something like a machine, some maybe robot or whatever, so that kind of produces observations of our random variable and inserts them into our sample. And these observations are produced by some theoretical probability distribution that is known to the robot, but not known to us. Right? So if we could really generate a lot of different samples from the true population, so like sample 1, sample 2, sample 3, and so on, sample 4, and apply leave one out cross-validation to the first sample, to the second sample, third sample, fourth sample, and so on, then this argument about different models that together compose together make the leave one out cross-validation, they are highly correlated. So because of this, this leave one out cross-validation estimates would be highly variable. The problem is that we cannot really see it in practice. So we can see it when we simulate the data set, but we cannot really see it in practice because, you know, the true population is not available in practice. But hypothetically, this is the case. And this is why leave one out cross-validation may not be good, not just from perspective that it is too computationally expensive, but it may not be good from the perspective that it has high variance. So this is the second issue with leave one out cross-validation as compared to k-fold cross-validation. So, and in practice, we just always use k-fold cross-validation with number of folds between 5 and 10. So it just use 5 or 10. So you don't even have to do anything in between, just 5 or 10. It will do. So here is a little quiz for you.